What happens if I run it? H. Oh! I've crashed it. Hello. Today I thought we'd chill out and do a bit of coding using my RC2014 and this rather nice little manual that I've discovered for the small computer monitor. So far I've been using CPM and trying to write code for that, but instead I thought we'd use something a bit more simple. So this is called a monitor. It's a type of interface for a computer that's not even an operating system. It understands some very basic commands. I can look inside sections of RAM. So if I do M and a number, I can see what's inside the memory. And I can just look at hex dump. And if I keep scrolling through, you can see up here it says small computer monitor and some words. I can also write code using this and disassemble the code. So I've already written some, and it's this bit here to about there, which I typed in earlier. So if I run that, you can see it writes a really nice little message. So I think I'll just play around with this and see what I can make it do. I've been following this tutorial for a bit just to figure out how things work. It's got lots of nice explanations in it. So I've been using this manual and I've had a go at these little programs. It says your first program, and it starts off by writing a single character to the screen and then writing hello world afterwards. It's all explained line by line. So what I've done is very carefully typed it in, and you've just seen on the screen it working quite nicely there. So let's just inspect that and have a look. So let's look at the help again. So if I do D for disassemble and I have to give it a memory location, it just dumps all that location on the screen and tries to interpret it as code, whether it's code or not. So fortunately, up to there, possibly here, I'm kind of forgotten where the code runs up to. That is actual code. This stuff here, complete garbage, could be anything. What I've also got in memory in a different place is this bit here. Now this is how computers actually work. If you look, it says hello world down the side here. But also, I've told it disassemble, so it's now trying to interpret this data as some sort of code. And it's not, it's data. But the computer doesn't know the difference. And that's the interesting thing with programming like this. If the computer isn't told when to stop running, it'll start running through any bit of memory until it hits the end or crashes, even if it's not instruction. So this is the monitor. Let's have a play around with it, try and figure out how to use this to write some code. I've got a little piece of code on the other screen, which we're going to type in. So this bit here. So what we'll do is we'll type in some code and then step through it and go around the computer's memory and find out what's in different sections. So the first thing to do is to tell it I want to assemble and a starting location, which is memory address 8000. That seems to be where everyone puts their code to begin with. And that's our tiny little program. So now the program's typed in. Let's disassemble memory location 8000. And if we look at the first section here, that's the code we typed in. And it's been converted into these hex digits. So you can see this 21 is this. So 3E must mean LDA. There's 02. So 0E must mean LDC. And then if you look, it says call 0030. Well, there's 0030, and it's backwards because that's how this computer stores its data. And then CD must mean call, and then C9 must be ret, which means return. So if I now tell it to execute that program, so you can see it's printed an exclamation mark. And if we look up here, it says 3E and then 21. This middle column is those 2 bytes, or 3 bytes, turned into ASCII text. So it's interpreted 3E as being a greater than sign, and 21 as being an exclamation mark. Well, 21 is an exclamation mark because that's what I wanted to print on the screen. If I was to edit 8000, and it says load A with 21, if I did LD A, comma, and we put in a different symbol, I think 22 should be a double quotes, because it's the next button on the keyboard. Didn't like that. What did I do wrong? Oh, I know what I did wrong. 3E 22. There, so now let's disassemble 8000. And there it is, double quotes. So I just got mixed up there between the assembly mode and editing raw memory, which is a really good point. This assemble thing is kind of a built-in option in the monitor that I'm using, where it will attempt to interpret the assembly code and turn it into the bytes that the computer actually understands. If I'm editing the memory, the computer doesn't understand what LDA means. It only understands the actual bytes of data. So when we edit things, we have to type in the actual bytes of data. So 3E is the command for LDA, and then 22 was the ASCII code for a double quote. If I type in 65 instead, that I think is a capital A. Let's find out. Do I know my ASCII table at all? Disassemble 8000. Okay, it's a small letter E, but it's a letter of the alphabet. That'll do. So now if I run that, we got an E. Now let's explore this. So disassemble 8000. LDA means load the A register with the number 65. LDC means load the C register with the value 2. Call means we're going to jump off to another piece of memory to do something else. Now that other piece of memory is location 30. So if I go and look at memory location 30, there it is. It's got this other command which is JP, which means jump. And that's got a memory location as well, so FE12. So let's go and look in that memory location, see what's in there. Memory location FE12 has another JP to this location. And if you look, there's quite a lot of other ones. So this is how basic low-level programs tend to work. They'll have a set of routines that are stored wherever they're stored in memory, and then a table of them that you can call into to access different bits of functionality. So I bet all these are different routines for doing other things with the computer, and this one is to do with writing text to the screen. So let's go look at 04FD. 04FD. And we have some code, which I don't know what it does. I've not inspected it in any great detail, but 04FD, let's have a think. Okay, if I disassemble my program, which is here, what I can do is maybe assemble line 8004, and I change that to be JP 04FD. So now I'm directly calling that piece of code that we've just found that was up here. This piece of code here. So now if we run the program, it should do the same thing. And it does. So another useful thing that this monitor can do is step through your code line at a time. So if I single step, it's shown me all the registers inside the computer. If I press enter, it's going to execute each line one after the other. So you can see the program counter was 8,000. We've just executed this instruction. It's 2 bytes long. So now the program counter's at line 8002. If I press enter, we've now executed these, and we've gone on 2, so now we're at line 8004. If you look, we put 65 in A, and then we put 02 in C. Well, the A here is the A register, and you can see it's now got 65 in it. I had 85, it's now got 65. The C register is here, and it used to have 72, and it's now got 02. We're now going to go to this 04FD, and unfortunately we can't go and poke around inside the monitor or the ROM using this debugger, so it runs it for me and it performs the output there. Right, I've had a quick Google and I've come up with some example simple programs, the kind of thing that you give a beginning programmer, and I think it might be quite fun to try and make these work. We've already done number 1, write a program that prints hello world to the screen. That's where everything starts. Next one is kind of the next thing that people do, write a program that asks for their name and then prints it back on the screen to them. Then there's one where it only responds to certain inputs. So number 1 is teaching you just how to print to the screen. Number 2 is doing user input. Number 3 is doing some sort of if. Number 4 is doing a loop. Number 5 is introducing some basic maths, like probably modulus. And then number 6 is doing some more maths. And from then on it just becomes a bit mathematical. This is how we used to learn programming back in the day. You spent quite a while just printing numbers to the screen and then making it print different numbers to the screen. So I think what we'll do is have a go at some of these. So what I've done is set up my screen slightly differently. I'm using Windows Terminal and the Windows subsystem for Linux, so I get a slightly nicer interface to do all this stuff with. The top pane is the Z80 machine, the bottom pane is just a text editor. Reason I'm doing this is because I can't save any code to the computer, so I may as well type in a text editor so I can at least save that later on. So what we're going to do is just have a quick mess around with this printing routine just to check that I've got that working. So what's in memory location 82100? It says hello world. Go 8000. Hello world. Marvelous. Right. We can print text. Next thing, user input. So I've read the manual and I've found these 3 lines of code which I think accept user input. So let's try and experiment with this. So the whole point of this is just mess around, figure stuff out. Later on we'll try and write something a bit more meaningful. So if I assemble from 8000. So step at 8000. So step through, put 1 in C. There's already 1, never mind. Right, so we want to put in something that we can see. So here's an ASCII table. Now, come back. So here's an ASCII table. Let's put in a lowercase t, and it should put 74. Right, so as you'll notice, it's in A. So the character you type in goes into the A register, 74. What happens if I run it? H. Oh, I've crashed it. Now, this is a problem with coding in assembly. At the moment, the computer just going through RAM, doing whatever, executing random stuff. It's got 64k of RAM to just run about in like a crazy thing, and because this is only a monitor program, there's nothing now checking the keyboard for me trying to press any sort of interrupt button. So the only thing I can do is restart the entire machine. Fortunately, it boots off ROM, and it boots that quickly. Even stranger is that the memory hasn't been reset. So if I look inside memory location 8000 again, my code is still there. How cool is that? And you can see all sorts of other rubbish. So it was doing all this kind of garbage before. So if you crash your computer and you just reset the CPU without clearing the RAM still contains what it contained before. As well, if I go to memory location 0 and execute it, it's like I've reset it as well. Yeah, okay, I understand. Right, disassemble 8000. So we've pushed that onto the stack. When it does a return, to know where to return to, it pops the return address off the stack. So it's just tried to go to the memory location of whatever hex character my key press is related to. So we need to just add a bit more code in here. Assemble to 8004. There, if we pop AF and then return, it should now run. So do that, T, push it, pop it, return, we're back. So this is why being able to step through your assembly code line by line is really, really useful. It lets you completely understand what should be happening. And all of this is actually also really useful to look at. So I can now read a character from the keyboard, and I need to put it into some memory. So I've been having a play around for a bit, and I've come up with this code, which works. It's a combination of a piece of looping code to print text, but instead of printing it, I'm storing text that's typed in. We're storing it at memory location 82100. We then have to call the built-in routine to read a character, which goes into the A register. Because I don't know if the HL registers get messed up or not, I've stored them and then restored them, because that's where we're looking at, that's our pointer into memory. We then comparing what we typed in with OD, which is the return key. If that matches, we're just going to return. Otherwise, we're going to store into the memory pointed at by HL the letter we just typed in, increment the pointer, and then jump, and I needed to calculate this memory location after typing it in, but we're trying to get back to here. So if we look at the code, here it is. So we're loading HL, we're then loading C, we're pushing, doing that thing and all this business. And then I'm jumping to 8003, which is this here. So this instruction takes up 3 bytes. I didn't know that, I had to type this in and watch this number changing. Everything underneath this is just garbage memory of whatever's in there. If we look at memory location 82100, you can see it's now got this in, because this was me testing it earlier. So let's run it again. Now you'll notice you can't see it on the screen, and that's because there's no code that I've written here to print it to the screen. So if I want to, I need to do that as well. So I might add that modification in a second. But now if we look at this location, you can see it's typed in. Now what it's not doing is putting a null terminating character at the end. So I'll need to modify the code for that as well. Right, I've done a bit more coding, had a bit of a think, learnt a few new things whilst going along, and I've got this piece of code. Not tested it yet, but in my head it should work. which is good enough, I think. So that's the pointer to the memory where we're going to store our data. This is the magicness that makes it get a key from the keyboard, put it in the A register. I can then compare the A register with enter. If it is, we jump to this bit of code down here, which puts 0 into the pointer to null terminate the string, then it returns. If it doesn't, we're going to put the key we typed in into the A register. We're then going to increment the pointer and then go back up to the start and have another go. So let's try it. Let's type in some stuff. Typing blind is quite hard. So let's look in 8100. I want a cup of tea, and then there's a 0, 0. That appears to have worked. Awesome. Right, so now we need to print out each character, or at least print the whole thing afterwards. Should we print the whole thing afterwards? Oops. That was just a case of adding this code here at the bottom. So let's try that. So I need to add some code to what I've already typed in. It's not a text editor. I can't just do what I'm doing down here and go around and start typing. I can't copy and paste. What I've got to do is disassemble the memory, have a look at it very carefully, and figure out exactly where in memory I will put the next instruction, which is going to be 8014. Instead of that return, we're going to put this. So 8014. So assemble 8014. Let's disassemble and have a look. Check it's all as it should be.
So done that. Right.
Go 8000. This is a test. Ooh, it's worked. That's quite cool. Right. I want it now to print out each character as I type it in. I don't want to use this code because that would, every time I press a key, it'll print out the whole string, but it's not null terminated, so it'll crash. So instead I just need the shorter code that I had previously that prints a single character. So I'm just going to go and find that. So I've now looked at a bit of documentation again, and to print a single character it needs to be in the A register. You then put 2 in the C register, do the I'm going to say BIOS, but it's not even a BIOS, is it really? Call the print routine and it should just print a single character. So the code needs modifying very slightly. It's almost like these are designed to go together. Look, you see, we put 1 in C, then we preserve HL just in case it gets mangled. We then call that routine to read the character, then we put 2 in C, call the routine again, and obviously 1 and 2 change how it works. Whatever this routine is at memory location 30, 1 means input, 2 means print a single character, and 6 means print a null terminated string. So now let's modify my code. And this is going to be really annoying now, because I need to insert a line of code, or 2. And you can't just insert lines of code. You have to retype out all the lines underneath it, I think. Yeah. So this is going to be slightly frustrating. Disassemble this. So where do we need to insert this code? Because everything after it will need retyping, which also means any memory locations will be different. So this is where I probably want to know how long each instruction is so I can pre-calculate this. Or use a real assembler that lets you use macros and things so that I don't have to hard code these in and the assembler itself can fill it in for me. But that's another time. Let's have a look. I'm going to pause you whilst I do this. Right, let's see if this has been typed in correctly. Have I actually put the right code in? So we're loading HL with the thing. Let's just get this up together. Put in C. Yeah. Push. Call the thing. Put 2 in. Now this is interesting. Doing LDC 02 takes 2 bytes. Incrementing takes 1 byte. So I could make my code 1 byte smaller, I bet, by just doing increment C. Because it needs to go from 1 to 2, and I could probably save a byte, which will make my program run a tiny bit quicker. Which is the fun kind of thing you can do when you can see the actual bytes that are making up the program. If you understand enough, you can make the program shorter. Shorter programs, less bugs, run quicker. Harder to understand though. Like this bit. I read in a book that is quicker than doing call 30, and it is only 1 byte instead of 3. But I don't understand why. I need to read more books. But is that in the right place anyway? So yeah. Compare it, jump to there. Load HL with A. Oh. That's the wrong instruction. 80OD should be a JPZ. Right. Assemble 80OD JPZ 8012. That's what that should be. Assemble. Now, when running that code, it wouldn't have told me that was the wrong instruction. It would have just done that and worked incorrectly. So I think that's working. Let's find out. Go 8000. HELLO. Can't delete. Delete will just insert a delete character. But then it may print the delete character and look like it's not there. Pressed enter. Did it do anything or have I killed it? I appear to have crashed it. Let's just reset the machine, because we now know that that doesn't wipe its memory. Mall computer monitor. I think the S got lost there in the reboot. Disassemble 8000. Jumping, if we press enter, to 8012, which then means I'm jumping back to the top. So the program hadn't crashed, it was just stuck in an endless loop asking for characters. I should have gone to 8015. Let's run it now. This is a test. And it worked, I think, because we've not made it print it out at the end after pressing enter, we've just null terminated it. So if we now look at that, there it is, and it's null terminated. Cool, that's worked. Okay, some time has passed. Ignore any blue on my fingers, I've just been painting the porch. Nice shade of light blue. Kind of matches the circuit board actually. My god, it's everywhere. Anyway, so I've added a bit more code now which should print out the string that we've typed in. let's run it. Maybe I should make it print another new line at the end of the input, just so you can see that it's happened. Right, let's try that then. So go 8,000. Okay. Okay, I've fixed it. Let's just have a look at the code. D8000. So what I had to do was change that, specifically that. So 0D is carriage return, 0A is line feed, or the other way around, I forget. Either way, it was printing out the text over itself because it had moved the cursor back to the beginning of the line, but hadn't gone down a line. So now if I run this, now you'll notice I typed in a few delete characters there, and it looks like it's deleted the text. Let's go and see what's stored in memory. So it prints it, which means it works. So now if I look at this, this is yet more text. Maybe I should. Then it says TA and then 2 dots, and it says start and my rising ing where I've fixed it. So if you look, there is a delete character, which I think is 08. So it's printing those, which moves the cursor back, and it's printing over itself again. And it looks like it's okay, but really it isn't. So I guess now what we need to do with this simple programming problem that we're trying to do, which is elementary. I ask my students at school to write programs that are way harder than this, and here we are spending most of the night figuring out how to write our name on the screen. Possibly doing it the most complicated way possible, but you know, this is kind of fun in a bizarre way. So it needs to ask the user for the name, and then say some sort of daft greeting with their name. So we need to store a string that says like, hello, what is your name? And then another string that says, nice to meet you, and then prints out their name. So maybe I store the prompt here, and I store the response underneath it, and then I store what they type in after that. So I'm going to do a bit of typing, have a think, and I'll come back when I've made most of that work. Right, here's what we're going to do. We're going to edit memory location 8100. Just checking that I'm not going to run out of space, because this code is getting longer. I guess as long as we don't go too far, it should be okay. Otherwise the code will start overwriting the data. Then we're in a mess. Right, edit 8100. Oh, I've not null terminated them. Well then. Edit 8100. Right, I think I've done it. Let's do some typing. Right, let's run. See if it works. What is your name? Ooh. Oh, it's worked. Aha! It overwrote itself though, which is annoying, and I can't be bothered fixing it. I think I'm done. Right, so I think that'll do for tonight. I've achieved quite a lot. I've gone from knowing absolutely nothing, like I didn't even know what the commands were. I had to find an instruction manual and print it so I could have it next to me to look at, and by copying and pasting bits of code from that together and then going through it line by line to understand how it works, I've managed to make a little program that does the good old what's your name and then prints out hello afterwards. So there we go. Right, so what we've learnt, if I disassemble the code, is that calculating addresses by hand is kind of annoying, but not too difficult on small programs like this. It actually reminds me of typing in BASIC. You know, it's always seemed to me that assembly and BASIC are very, very similar. It runs top to bottom, and the only way of doing anything else is by jumping to specific parts of memory that are like addressed by a location with a number. So clearly BASIC is just assembler, but with more words than interpreted, so that's like interpreted assembler, which sounds terrible. But what I've got is a nice little program that I can't save, so I have to type it in here. And if you're curious, this is the same program, right? Let's see. Name equals input. This is your name. Wait, what? Oh, Python 2. Oh god. Hang on. Python 3. There we go. 2 lines of Python, and an equivalent thing in Z80 is quite a bit longer. But that's what this turns into, really. That's what I like about this. I've been able to learn assembler very directly by typing in, running it, seeing it not working, and then typing something else in to fix it. I've not had to compile it, copy onto an SD card, put it in a different machine, reboot it, see what's not working, try and figure it out by doing printfs everywhere. I've been able to step through the assembler instruction by instruction and fix it and actually understand how the program is working and what the computer's doing. And this is really, really good. It's like a really quick way of learning something. There's that instant feedback of if it's right or not. It is very similar to using an interactive thing like Python or the old BASIC that was on here. So I'm going to use this some more to learn a bit more Z80, but I do need to find a better assembler. I need something that is a bit more kind of modern, so that I don't have to figure out memory addresses by typing it out and then looking it up and typing it back in. I want to be able to use macros or labels. So yeah, right, well this has been quite fun. I think in the next video I'll do some more hardware stuff, poking around at this little computer using an Arduino, maybe feeding some code directly into it, because what I've got now is some of this, and I can stick it on a chip, maybe, because I've got an EEPROM programmer, and try and make it run it using as few parts as possible. Right, well, I'll see you later.